somewhere in the warm, near-vertical drop of water off a small volcanic island in the eastern Caribbean, a machine has spent years listening to something no human ear ever fully understood. It has absorbed millions of underwater recordings, sharp rhythmic clicks that sailors for centuries heard echoing through the hulls of their ships and dismissed as nothing more than the ocean making its own noise. Buried inside that mountain of data, artificial intelligence has now found something that looks less like animal noise and more like structure. Repeating units. Rhythm. Timing that shifts in small, deliberate ways. Elements that behave, in a strange and unsettling sense, like vowels. Researchers working on the project have described the moment those patterns first became undeniable as one of the strangest in their careers. A slow creeping realization that what they had spent years calling background noise might actually be closer to a conversation happening right beneath the hulls of every ship that had ever sailed past. That is where this story starts. It is not, however, where it ends, because once scientists began mapping the shape of that communication system, a far stranger and far more uncomfortable question opened up underneath it. If these animals have been exchanging structured pattern signals across families and generations for millions of years, then what exactly have they been saying to one another all this time, and why does even a partial answer leave some of the people who found it a little unsettled? To understand why this research has landed as hard as it has, you first have to understand how small we assumed these creatures were in every way that actually mattered to us. For most of human history, people looked at whales and saw one thing above everything else: resource. A mountain of flesh, oil, and bone drifting beneath the surface, waiting to become lamp fuel, corset stays, and machine grease. Entire coastal economies rose and fell around the hunt. When a whale surfaced beside a wooden boat and let out one of those long, aching cries that seemed to vibrate straight up through the timbers, nobody on deck assumed they were hearing anything close to a sentence. They assumed they were hearing an animal, an enormous and mysterious one, but an animal running purely on instinct, the sound as empty of intention as wind moving through a canyon. Even the people who admired whales tended to admire the wrong thing. They marveled at scale. A blue whale stretching longer than 3 school buses laid end to end, a heart roughly the size of a small car, arteries wide enough that a child could theoretically crawl through one. Cliffside observers gasped at a breach, at a fluke slapping the water like a gunshot. But the fascination stopped at the body. Almost nobody seriously entertained the idea that behind those ancient eyes sat a mind capable of something resembling language, because the notion felt almost like science fiction. A creature that large, most assumed, had to be running mostly on plumbing and reflex. So the haunting sounds rolling up from the deep stayed exactly what an earlier era had decided they were the first time anyone heard them. Beautiful, empty noise, gorgeous but meaningless, the soundtrack of a world with nothing in particular to say. That certainty held firm until the early 1970s, when a small group of researchers, led by biologist Roger Payne, lowered hydrophones into the water off Bermuda and began actually paying close attention to what they were recording. What came back should not, by the standards of the time, have existed. Humpback whales were not simply moaning at random. They were singing, and not in the loose poetic way people describe birdsong. In a genuinely structural sense. The sounds arrived in phrases. The phrases repeated. The phrases combined into themes, and the themes stacked into full songs that could run for 20 minutes, sometimes much longer, before looping back to the beginning and starting again. And the detail that unsettled researchers most was that the songs changed. Season after season, an entire population of whales in a given ocean would gradually revise its song together, dropping old phrases, introducing new ones, until every individual in the group had adopted the update. A shared, evolving composition passed between individuals the way a melody moves through a crowd. Instinct does not typically rewrite itself on a schedule like that. What Payne had captured looked, unmistakably, like something closer to culture. Those recordings were pressed onto vinyl and released to the public as an album called Songs of the Humpback Whale, and the reaction was extraordinary. People listened, and many of them wept. There was something in those long, spiraling cries that cut past every assumption humanity had carried about these animals and grabbed listeners somewhere they didn't expect. It didn't sound like an animal making noise. It sounded like longing, and it moved people in a way no scientific paper ever could have. That single record helped ignite a global conservation movement, one that played a real role in the fight to end large-scale commercial whaling and pull several species back from the edge of extinction. The sound of the whales, in a very real sense, helped save the whales. And yet for all of that emotional power, one enormous question remained completely unanswered. Humanity had been moved by the whales. It still had almost no idea what any of it actually meant. That unanswered question gave rise to an entire field, bioacoustics, the study of animal sound, and for decades that field lived in a frustrating in-between space, rich in beauty and starving for meaning. Researchers spent months, sometimes years, sitting with headphones clamped over their ears, replaying the same recordings again and again, trying to catch a repeating shape through sheer human patience. The tools available were painfully limited. A person can only hold so much sound in working memory at once, gets tired, gets bored, misses a click that lands a fraction of a second early. And even when a real pattern was found, even when researchers could confidently say this whale makes this particular sequence of clicks and that whale answers with something similar, they slammed into the same wall every time. What did it actually mean? Was it a name, a warning, a greeting, something with no equivalent in human experience at all? Scientists could transcribe the music note for note and still not read a single line of it. It took a marine biologist willing to question the entire approach to move the field somewhere new. David Gruber had spent years around whales and had come to feel, in a way he couldn't fully justify with data, that something enormous was slipping through the field's fingers every single day. He would watch a pod move through open water in perfect coordination, adjusting behavior in real time, responding to each other across distances too great for eyesight to bridge, and he couldn't shake the sense that he was standing in the middle of an active conversation he simply lacked the instruments to hear. The more he sat with that feeling, the more he suspected the problem wasn't the whales at all. The problem was the toolbox. Every researcher before him had approached whale sound strictly as biology, as behavior to be logged and counted, and Gruber began to wonder if that framing itself was the cage holding the entire field back. So he looked somewhere unexpected. Around 2018, while a fellow at Harvard's Radcliffe Institute, Gruber found himself sharing space with dozens of researchers from wildly different disciplines, including Shafi Goldwasser, a Turing Award-winning cryptographer whose team was working on machine translation, exploring how software could learn to translate between two human languages not through a dictionary or a shared reference point, but by mapping the underlying mathematical shape of each language and finding where those shapes overlapped. Gruber had a realization that would end up reorganizing his entire career. What if the same approach used to translate between human languages with no shared vocabulary could be pointed at a species that had no human vocabulary at all? What if the search for another intelligent voice didn't require pointing instruments at the stars, because the voice in question was already here, swimming beneath the surface of our own planet, wrapped in a body of muscle and blubber, carrying a brain several times the size of a human's, and had been trying to be heard the entire time? That reframing lit a fuse. The moment you stop treating whale sound purely as animal noise and start treating it as a structured signal worth decoding with the same mathematical seriousness applied to unsupervised language translation, a different set of tools suddenly becomes relevant. Machine learning models that can find hidden structure in enormous, unlabeled datasets. Systems that don't get tired, don't get bored, and can hold millions of recordings in active comparison at once, hunting for architecture no single human listener could ever catch by ear alone. Gruber's real contribution wasn't a new piece of hardware. It was a new belief that this had never been decorative background noise, and that the field had simply lacked the tools and perhaps the humility to take it seriously as a genuine communication system. Out of that belief, in 2020, a non-profit initiative was born with catalytic funding from the TED Audacious Project, and it was not a modest undertaking. Gruber called it Project SETI, short for the Cetacean Translation Initiative, a name deliberately built to echo an older, more familiar acronym, SETI, the decades-long search for extraterrestrial intelligence. But SETI's ambitions went further than simply listening. The stated goal was to build a genuine understanding of sperm-whale communication rich enough that meaningful two-way contact might eventually become possible, to not only decode what these animals were saying but to have some hope, eventually, of responding in a way that could be understood. Studying sperm whales seriously is about as difficult a scientific undertaking as exists. The whales most worth studying, with their complex layered click patterns, spend the overwhelming majority of their lives in a place human beings physically cannot follow, diving thousands of feet down into cold, crushing, lightless water where no diver can go and cameras struggle to see anything at all. They range across enormous stretches of open ocean, surfacing for only a handful of minutes before disappearing back into the deep. You cannot hand a whale a microphone, ask it to repeat itself, or reliably tell from a boat which individual in a group made a particular sound or who that sound was even meant for. Nearly every advantage a human researcher normally relies on disappears the moment you enter the whale's world. Which is why the first major decision the project made wasn't about algorithms at all. It was about geography. If researchers could not follow whales into the deep, they needed a place on Earth where the deep essentially comes to the surface, where sperm whales choose, for their own reasons, to live close enough to shore that a small research boat has a real chance of being present when they communicate. Such a place exists. Just off the coast of Dominica, a small, rugged, volcanic island in the eastern Caribbean, the seafloor doesn't gently slope away the way it does off most coastlines. It drops, almost vertically, into water thousands of feet deep within a mile or two of shore. As a result, roughly 200 sperm whales live in matrilineal family groups close to Dominica's coast for much of the year, hunting and raising calves in water a research vessel can reach in minutes rather than days. For a team trying to eavesdrop on one of the hardest-to-study animals on the planet, it amounted to a rare scientific gift. Long before there was any artificial intelligence involved, and long before there was any significant funding, there was a single researcher in a small boat off Dominica, learning to recognize individual whales the way a person learns to recognize the faces of an extended family. His name is Shane Jarrow, a biologist who founded the Dominica Sperm Whale Project years before SETI existed and who eventually became the initiative's biology lead. Jarrow spent well over a decade getting to know this specific population as individuals rather than statistics. He gave them names. He tracked matriarchs, watched calves being born and grow into adults, learned which family units traveled together and which kept their distance, and recorded their clicks patiently for years without any real ability to decode them, driven mainly by the conviction that something meaningful was happening in that sound whether or not the tools existed yet to prove it. That decade of quiet, patient observation became the actual foundation the entire project would eventually be built on, because an artificial intelligence model, however powerful, is only ever as good as the data and context it's given. When a machine later flagged a particular pattern of clicks as significant, it mattered enormously that a human researcher could say that came from this specific whale, the daughter of that specific matriarch, recorded while her family gathered at the surface after a long dive. The algorithm could find the pattern. Only years of human familiarity could give that pattern any context at all. Around Gruber and Jarrow, an unusually wide team assembled, marine biologists who understood the animals, machine learning researchers from institutions including MIT and Imperial College London, linguists who understood how language itself is structured, roboticists who could design equipment gentle enough not to disturb the whales, and cryptographers experienced in finding structure inside unfamiliar data. It is a group of specialists who, under ordinary circumstances, would almost never end up working the same project, united here by an unusually ambitious shared goal. Knowing individual whales and actually reaching them at scale, though, were two very different problems. The core obstacle never went away. You cannot ask a whale to hold a microphone. So the team did the next best thing and filled the ocean itself with microphones, building something that had never existed before, a permanent, always-on underwater listening array anchored to the seafloor off Dominica, eventually spanning roughly 20 kilometers by 20 kilometers of ocean. Rather than recording for a single afternoon expedition and hauling the equipment back up, the hydrophone grid ran continuously, day and night, capturing every click that passed through that stretch of water. Because sound travels through water at a known, measurable speed, and because each hydrophone in the array picks up a given click at a very slightly different instant, researchers could work backward from those tiny timing differences and triangulate the precise three-dimensional location a sound had come from. The array didn't just hear the whales. It located them, identifying not just that a click had occurred but which whale at which depth and position had made it, and which other whales were nearby to hear it. Even that wasn't enough on its own, because knowing who made a sound only answers half the puzzle. The far harder half is why. A given click pattern might carry an entirely different meaning depending on whether a whale is plunging into a hunting dive or floating calmly at the surface beside its calf, and sound data alone cannot distinguish between the two. To connect vocalization to context, the team turned to soft, non-invasive robotics, designing small suction cup tags, using the same basic physics as a bathroom hook, that could be gently attached to a whale's back without piercing the skin, recording audio alongside heart rate, and the pitch, roll, and diving angle of the animal's entire body before popping free and floating to the surface for retrieval. With that data layered in, researchers could finally line up a specific string of clicks with the exact physical situation surrounding it. One pattern recorded during a steep, muscular hunting dive with an elevated heart rate, another softer, differently spaced pattern recorded hours later while the same whale rested calmly at the surface with a calf pressed against her side. Behavior gave the sound a shape, and gave the eventual machine learning models something they desperately needed, a plausible why to sit next to every what. By the time the project's archive had grown into the millions and then billions of individual recorded codas, the largest library of whale sound ever assembled, the team converted each recording into a spectrogram, a visual map that plots time along one axis and pitch along another, turning a click into a mark and a rhythm into a visible texture. Neural network models, trained the way a child absorbs language, by pattern exposure rather than an explicit rulebook, were set loose on these images with no answer key, simply instructed to look for structure. And they found things no human ear had ever caught on its own. In 2024, the team announced they had identified what they described as a sperm whale phonetic alphabet, a set of around 4 to 5 basic rhythmic and tonal building blocks, roughly 150 distinct codas built out of them, that whales appear to combine and recombine the way human speech combines phonemes into an effectively unlimited range of words. A follow-up study in 2026, led by SETI researcher Gaspar Bigas and published in the Proceedings of the Royal Society B, went a step further, identifying that when the silences inside individual codas are stretched out, the underlying clicks contain elements that function acoustically similarly to human vowel sounds, at least 2 distinct whale vowel-like sounds so far, some of which shift within a single coda the way a diphthong shifts across a human vowel, the way the word cow glides from one vowel sound into another. None of this means whales have been proven to have a language equivalent to a human one, and the researchers involved are careful to say so publicly. What they have found is real evidence of combinatorial structure, building blocks that can be assembled and reassembled to produce variation, layered rhythm and tempo changes that appear to carry social meaning, and now sounds with vowel-like acoustic properties, findings serious enough to be published in leading peer-reviewed journals. Translating any of that into concrete meaning, actually knowing what a specific coda communicates the way a dictionary defines a word, remains a much harder and still unfinished task. One Gruber has said may require analyzing billions more recorded codas before the picture becomes clear. What has changed is the confidence with which scientists can now say this is not empty noise. It has architecture. It has rules. And it may be far closer to the outer edge of what we call language than almost anyone in the field was willing to say out loud a decade ago. That is the part that unsettles people who spend their careers thinking carefully about what separates human minds from every other animal on this planet. For most of recorded history, the capacity for structured, combinatorial, culturally transmitted communication was treated as something close to a defining line around our own species, the trait that set us apart from everything else alive. If sperm whales have been carrying a system with even some of those same properties through the dark for millions of years, quietly, in a medium we spent most of our history unable or unwilling to listen to closely, then that line was never as solid as we assumed it to be. It doesn't mean the whales are secretly plotting anything, and it doesn't mean a full whale-to-English dictionary is right around the corner. What it means is smaller and, in its own way, more disquieting. An entire intelligence has apparently been carrying on a rich, structured conversation just beneath the hulls of every ship that has ever sailed past it, and until very recently, we simply weren't equipped to notice. So here is the question worth sitting with. If whales have been carrying something this close to language across millions of years, all while an earlier era of humanity dismissed it as empty noise, what do we actually owe them now that the evidence says otherwise? Tell me what you think, and stay a while, because there is a great deal still moving through the dark that science is only beginning to make sense of.